Hello everybody, and today we have experiment 1 for the CH326 labs. It's the Hantzsch pyridine synthesis, the preparation of 1,4-dihydropyridines. And we'll be dealing with some practical techniques, product purification by recrystallization, and TLC, where we look at solvent strength and retention factors. Okay, so some learning outcomes. By the end of the practical, you should be familiar with a recrystallization to purify a solid. You should understand what mobile phase strength in chromatography means. You should be able to predict how changes in the mobile phase strength affect retention times or retention factors in chromatography. And you should be able to work out the number of equivalents in a chemical reaction. So the reaction we're dealing with today is part of the Hantzsch pyridine synthesis, which goes all the way to compound B. We will just be dealing with the synthesis of compound A here, a 1,4-dihydropyridine. And you can see mechanisms relating to this chemistry in organic chemistry by Clayton in chapter 30. Okay, there's a few steps to this synthesis, and you can see on the left here we have our different starting materials, and there we have our 1,4-dihydropyridine compound A on the right. And you can see we have them color coded, so you can see where the atoms map onto the product in terms of red mapping to red, blue to blue, purple to purple, and black to black. Okay. So there's 5 key steps for this mechanism. The first is a keto-ester enolate formation. Then we have step 2, an aldol condensation between the aldehyde, in this case formaldehyde here at the top, and the keto-ester enolate to form an enone. We then get step 3, which is Michael conjugate addition of another keto-ester enolate to the enone. Then step 4, addition of ammonia to one ketone, and cyclization of the imine or enamine to the other ketone. So here we'll break down this a little bit more. And step 1 is keto-ester enolate formation of the keto-ester in red. And then we get an aldol condensation between the enolate from the keto-ester in red to the formaldehyde. And that forms this intermediate compound here. You see this alpha-beta unsaturated ketone. We then get a Michael addition of the enolate from the blue keto-ester to the product of our first step. So we get our Michael addition to give us this intermediate. And then step 4, we have addition of ammonia to one of the ketone groups. And then we get cyclization across to close the ring and give us compound A. So in the write-up, you will be expected to give the mechanisms for steps 1, 2, and 3, but not for 4 and 5. And you can simply state that at that point you get an addition of ammonia and cyclization to give the final product A, a 1,4-dihydropyridine. When we're doing any experiment, we need to be very conscious of health and safety, and we have our safety data sheets that we would go through. Here's just an example of some of the safety information that's in your lab manual. So even though this is an online experiment this year, it is still important for you to read over the safety data and be familiar with thinking about the safety of doing an experiment. So the procedure in this experiment for the preparation of our 1,4-dihydropyridine. So first of all, we're going to place 6.5 grams of ethyl acetoacetate, 3.9 grams of ammonium acetate, and 5 ml of formaldehyde from a 40% aqueous solution of formaldehyde in a 100 ml round conical flask that contains 10 ml of ethanol. And what we'll see then is an exothermic reaction occurring. That means it gives off some heat. The mixture is then gently warmed on a hot plate for 15 minutes and then allowed to cool for a few minutes. We add approximately 25 ml of cold water and cool the mixture on an ice bath until precipitation is complete. The solid product is filtered off using suction filtration and recrystallized from 95% ethanol. So that's 95% aqueous ethanol. To carry out the recrystallization, you dissolve the crude product in a minimum amount of hot ethanol to form a supersaturated solution. When all the crude product is dissolved, you allow the solution to cool down. A crystallization will occur and you filter the recrystallized product with a Buchner funnel. You record the yield and the melting point. So just a little bit further comment about one of the techniques we're meeting, and that is recrystallization. So it's product purification by recrystallization. So recrystallization is a procedure used to purify solids by removing impurities of different solubility. And the method consists of dissolving the solid in just sufficient boiling solvent to make a hot saturated solution. And you filter the hot solution to remove insoluble impurities if there are any present. You cool the filtrate and allow it to stand until crystallization is complete. You separate the crystals from the mother liquor by filtration. and then you wash the crystals with a little cold solvent to remove any adhering solution. And finally, you dry the crystals. Another practical technique we're meeting today is the evaluation of purity by TLC analysis. So within TLC, we're going to discuss solvent strength and retention factor. So when we're running our TLC technique, we will typically have a beaker with a glass, watch glass on top, and we have our TLC plate. And with our TLC plate, we'll draw a pencil line along the bottom, and we'll put a spot of our product mixture, our reaction mixture, onto the pencil line. We have our solvent system in our beaker, and the solvent system must be below the pencil line. We place our TLC plate into the beaker, put on the watch glass lid, and the solvent system will move up the TLC plate. When the solvent front has reached the top, about 1 centimeter, we mark it with a line, and we take out the TLC plate and then we mark it with a line. We visualize it under a UV lamp, and we should be able to see our compound spots. We want to measure the distance from the baseline to a compound spot and from the baseline to the solvent front. We divide the distance from the baseline to the compound spot by the distance from the baseline to the solvent front. So in this case, 4 divided by 5.5. And that gives us our retention factor. And when you quote retention factors, you also have to quote the solvent system you used, because you will get different retention factors in different solvent systems. There's a link here which you can use to look up other information, additional information on thin layer chromatography, TLC. In terms of the mobile phase strength, we want to comment a bit more about that. So the ability of the mobile phase to compete with the stationary phase for the analyte is known as the mobile phase strength. In NPC, which is normal phase chromatography, the stationary phase is polar, such as silica gel, and the mobile phase is non-polar, such as organic solvents. A strong mobile phase has a high percentage of high polarity solvents. In reverse phase chromatography, the stationary phase is non-polar, such as a C18 column that you might use in HPLC. The mobile phase is polar, typically a homogeneous mixture of water and organic solvents, such as water and acetonitrile. And a strong mobile phase has a high percentage of organic solvent. The TLC system we're going to be using is more like normal phase chromatography, where we have a polar stationary phase like silica gel, and we use non-polar organic solvents as our mobile phase. The mobile phase strength affects the retention time of the analytes, how far the spot moves up the TLC plate. Optimal separation of the components of a mixture can be achieved by adjusting the mobile phase strength. So if you have 2 or more components in your reaction mixture, you will want that to separate on the TLC plate to show you at least 2 spots, 1 spot for each component. In order for them to separate, you will need to adjust the mobile phase to give the optimal separation. Adjusting the mobile phase strength means mixing the solvents in different percentages. So let's look at an example. Here we have an example where we have petroleum ether and diethyl ether in a 1:1 ratio as our mobile phase. And this is the TLC plate that results. The compound spot moves 4 centimeters up the plate, and the solvent front has moved 5.5 centimeters up the plate. Let's change the solvent system, the mobile phase, to a 3:1 ratio of petroleum ether is to diethyl ether. Now the compound spot only moves 2 centimeters up the plate. Why is this? Well, in the first system we had a higher mobile phase strength. So that means the mobile phase is better able to compete with the stationary phase for the analyte, and the analyte spot moves further up the TLC plate. So in this experiment, you want to analyze the purity of your recrystallized product using TLC. So to do that, we're going to prepare a sample of the product by placing a very small amount, the tip of a spatula, in a glass vial and dissolving it with 2 mL of ethyl acetate. We then prepare the mobile phase. Our mobile phase is going to be cyclohexane is to ethyl acetate 1:3. We spot our product on the TLC plate and run them on the above mobile phase. We're going to visualize the spots on the UV lamp and record retention factors for product A in that mobile phase. When reporting a retention factor, you must also report the mobile phase. So, in the write-up, you will need to write up various aspects of the experiment that you will have seen on the video and that we have discussed in this talk. There are also questions that you need to answer as part of your write-up, and they're very important to complete as there's a substantial amount of marks going for them. So this is just a reminder of that. We have question 1, question 2, question 3, question 4, and question 5. In relation to the write-up itself, here are sections that will be marked in your write-up. So it needs to include, it's your normal lab write-up that you would normally done, same as you would have done in CH326A-1, and you need to include a reaction scheme and table, reaction mechanisms, experimental methods and procedures, theoretical yield in grams, the presentation of results, and the answers to your questions 1, 2, 3, 4, and 5. In terms of the presentation of results, I expect to see a physical description of the product, the percentage yield of pure product after crystallization, and any comment to explain why there might be a difference between 100% yield and the yield you found. I want you to report the melting point range. If we were doing this in the lab, we would record a melting point, but I just want you to note the literature melting point of this compound in your report. You also need to explain and discuss the TLC work, the retention factors, and obviously mentioning the mobile phase that was used. And in all cases, I need you to show your workings and calculations. Also, just a reminder about the reaction table that you need to include. Here's an example. And of course, you need to include molecular formula, molecular weight, the moles amount to be used, mass to be used in grams, density, volume to be used, limiting reagent, yes or no, number of equivalents to be used, the theoretical yield in moles, and the theoretical yield in grams. Okay, that concludes our lab talk for today for the Hantzsch synthesis, where you are synthesizing 1,4-dihydropyridine. Please watch the video and watch and look up the various links on Moodle, and I will see you in the question and answer session later on in the lab class. Thank you, everybody.